Good morning, students.
Good morning, ma'am.
Okay, so in previous session we discussed about the AC voltage through inductor. So all of you please, now we can quickly recall all the equations regarding with that of the AC voltage through inductor. So starting with Nandana, equation for current that is generated in an inductor when it is connected to AC voltage source.
Im sin omega t minus 90.
I is equal to Im sin omega t minus 90. Anna, equation for power.
P, ma'am, instantaneous
Value of power.
Pm by Im by 2 into sin 2 omega t.
Vm Im divided by 2 minus Vm Im by 2 into sine 2 omega t. Then what about the average value of power, Sania?
Minus Vm Im by 2 in and 2 omega.
It is the average value of power that is generated in an inductor. Average value of power.
0.
Average value of power is equal to 0. Okay. So the instantaneous value of power is given by P bar is equal to minus Vm Im divided by 2 sine 2 omega t. But the average value of power over a complete cycle in the case of an inductor when it is connected to an alternate voltage source is equal to 0. Okay. So that's all about the. Okay. So that's all about the AC voltage through the inductor. Now we are going to discuss AC voltage through the next electrical component, that is capacitor. Okay. So all of you write the next heading, AC voltage through capacitor. AC voltage through capacitor. Consider a capacitor. Consider a capacitor with the capacitance C. Consider a capacitor with the capacitance C, and it is connected to an alternative source of EMF, and it is connected to an alternative source of EMF. V is equal to Vm sin omega t. Consider a capacitor of capacitance C and it is connected to an alternative source of EMF. V is equal to Vm sin omega t. So the same alternative source of EMF V is equal to Vm sin omega t that we are used in all these three cases, that is in the case of resistor, inductor and capacitor. The alternative source of EMF is the same, V is equal to Vm sin omega t. The variation takes place only in the case of current that is generated in this electrical components. Okay. So here we consider a capacitor with a capacitance C and it is connected to an alternative source of EMF. V is equal to Vm sin omega t. Now draw the diagram. So here we replace the electrical component inductor by capacitor. Capacitor is represented by two parallel lines. It is connected to an alternative source of EMF. V is equal to Vm sin omega t. What do you mean by capacitor? What is capacitor?
To store
To store what? To store?
current.
Is it store the current? Okay, or to store it is used
Energy.
to store the energy storing device, or it is a device that is used to store the electrical charges. Okay, so capacitor is a device that is used to store the charges. So here we are discuss about these capacitors and the charge developed in a capacitor in our previous chapter, that is in the current electricity. That we are in the third chapter, current electricity. We are already discussed about the properties of capacitor and the equation for the charge developed in a capacitor when an alternative source of EMF is connected to it and all. So here we are connecting an alternative source of EMF V is equal to Vm sin omega t to a capacitor with a capacitance C. Then the charge that is stored by the capacitor is given by, then the charge stored by the capacitor is given by what is the expression for the charge stored by capacitor? Equation for capacitor, equation for charge that is stored by the capacitor is given by, which letter that we are used to represent the charge?
Q.
Q. So Q is equal to,
C.
yeah, Q is equal to CV, where Q is the charge, C is the capacitance of the capacitor, V is the potential. So here we start our derivation by considering the charge stored by the capacitor. Whenever an alternative source of EMF V is equal to Vm sin omega t is connected to a capacitor, then the charge stored by the capacitor is given by the equation Q is equal to CV. But here we want to find out an expression for the current generated in a capacitor when it is connected to an alternative source of EMF. V is equal to Vm sin omega t. So from this expression, how we can generate an equation for current developed in a capacitor? Q is equal to CV. From this equation, how we can generate an equation for current developed in a capacitor? What is current? What do you mean by current?
Rate of flow of charge.
Rate of flow of charge. That is, charge by time is known as current, right? So the rate of flow of charge is known as current. So here we need to find the derivation of this equation. Then only we get an expression for the current. Okay, so by derivation we get, or write the equation like the current generated in a capacitor is given by, current generated in a capacitor is given by rate of flow of charge, that is dq by dt. dq by dt is equal to d by dt of CV. The charge stored in a capacitor is given by Q is equal to CV. But here we didn't want any expression for the charge stored in a capacitor. We want to calculate the current that is generated in a capacitor when it is connected to an alternative source of EMF. V is equal to Vm sin omega t. So from the first equation, we can find out an expression for current by the relation between the current and the charge. We know that the electric current is nothing. It is the rate of flow of charge. The rate of flow of charge is known as electric current. So we need to find the derivation of the first equation. Then only we get an expression for current. So dq by dt is equal to d by dt of CV. We just find the derivation of both LHS and RHS. Or we can write dq by dt is equal to, here the C is the capacitance of capacitor. It is a constant. We can take it outside. So it becomes C into dV by dt. dq by dt is equal to C into dV by dt. So here where Q is the charge, dq by dt means rate of flow of charge. The derivation of charge with respect to time. C is the capacitance and V is the applied voltage. So dV by dt means here we are applying an alternative source of EMF. So instead of that symbol V, we need to substitute Vm sin omega t. So the equation becomes dq by dt is equal to C into d by dt of, instead of the V, here V is the applied voltage. In the present case, we are applying an alternative source of EMF, V is equal to Vm sin omega t. So instead of that symbol V, we need to substitute C into d by dt of Vm sin omega t. Again, what is dq by dt? Derivative of charge. Derivative of charge gives the value of rate of flow of charge is known as dash. Current dq by, yes, I, dq by dt is indicates I, the value of current that is flowing through a capacitor when it is connected to an alternative source of EMF. V is equal to Vm sin omega t. So here dq by dt is equal to I. I is equal to C into d by dt of Vm sin omega t. So here Vm is a constant. A constant value of EMF is passing through this capacitor. So we can take this term outside. So it becomes Vm into C into d by dt of sin omega t. I is equal to Vm into C d by dt of sin omega t. In trigonometry, d by dt of sin ax. What is the value of d by dt of sin ax? Or instead of this ax, I think it is better d by dt of sin 2 theta. What is the derivative of sin 2 theta? No idea. The derivative of sin 2 theta, that is d by dt of sin 2 theta is equal to cos 2 theta into 2. This is the solution for d by dt of sin 2 theta, that is cos 2 theta into 2. Similarly, here we have another function sin omega t. So d by dt of sin omega t is equal to cos omega t into omega. So the expression becomes I is equal to VMC into d by dt of sin omega t is cos omega t into omega. So this is the general equation that we are used here to solve d by dt of sin omega t. The derivation of sin ax, d by dt of sin ax is equal to cos ax into a. Similarly, instead of this ax, here we have omega t. So d by dt of sin omega t is equal to cos omega t into omega. So the equation becomes I is equal to Vm into C into cos omega t into omega. So now we can just rearrange this equation. It becomes I is equal to Vm C omega into cos omega t. By rearranging the equation, we get I is equal to Vm C omega cos omega t. Or we can write I is equal to Vm into 1 by C omega. So in effect, it becomes C omega itself. So we can write I is equal to Vm into 1 by C omega into cos omega t. So this C omega is represented like this. C omega is equal to, we are replaced it in the form of 1 by C omega. So I is equal to Vm into 1 by C omega into cos omega t. And this 1 by C omega is equal to chi C. 1 by C omega is equal to chi into C. Chi C, not chi into C, chi C. 1 by C omega is equal to chi C. Where this chi C is indicates capacitive reactance. So in the case of inductor, the chi L is represent inductive reactance. Similarly, in the case of capacitor, this 1 by C omega is equal to chi C. This chi C indicates capacitive reactance. The term chi C indicates capacitive reactance. And capacitive reactance means it is the resistance offered by the capacitor. Chi C is actually an equivalent term than similar to that of the resistance in the case of a resistor, or chi L in the case of an inductor. Similarly, in the case of capacitor, we have a term chi C that is representing the capacitive reactance, that is the resistance offered by the capacitor. So here 1 by C omega is equal to chi C, where chi C is the capacitive reactance. So our equation for current becomes I is equal to Vm into 1 by C omega. So instead of this 1 by C omega, we can substitute this chi C. So 1 by chi C into cos omega t. Or I is equal to Vm by chi C into cos omega t. Then can you guess what is this term Vm by chi C represents? According to Ohm's law, generally we have I is equal to V by R. I is equal to V by R. That is in the case of resistor, according to our Ohm's law. In the case of inductor, we have Im is equal to V by chi L. Similarly, here we have another expression, Vm by chi C. What is this Vm by chi C represents?
Im.
Im, that is equal to Im. Okay, so this term Vm by chi C is represent Im. Here, Vm by chi C, where V is the potential and chi is the capacitive reactance. That is nothing, it is the resistance offered by the capacitor. That is potential divided by the resistance, that is equal to the value of current I. So it becomes Im. So here Vm by chi C is represents Im. So the expression for current becomes I is equal to Im cos omega t. I is equal to Im cos omega t. So this is the expression for the current generated in an AC voltage through a capacitor. In the case of inductor, it is I is equal to minus Im cos omega t. But here in the case of capacitor, it is I is equal to Im cos omega t. Positive Im cos omega t. And we know that the expression for EMF is V is equal to Vm sin omega t. That is, EMF is in terms of sine function. So we need to convert the current also in terms of sine function, because alternative current is a current that is varies sine functions with respect to time. So here we are going to convert this cos function in terms of sine function. What is cos theta? Cos theta is equal to sin 90 plus theta. Sin 90 plus theta is equal to cos theta. So similarly here we have cos omega t. Cos omega t is equal to sin 90 plus omega t, or you can write omega t plus 90. So according to trigonometry, we know that cos theta is equal to sin 90 plus theta. Similarly, here we have the phase angle omega t. We can write sin 90 plus omega t or sin omega t plus 90. So the expression for current becomes, in terms of sine function, it is I is equal to Im sin omega t plus 90 or 90 plus omega t. Both are right. Sin 90 plus omega t. So this is the real value that we are obtained whenever an alternative source of EMF V is equal to Vm sin omega t is applied to an capacitor with the capacitance C. The current generated is given by I is equal to Im cos omega t. But we know that alternative current R varies as a sine function with respect to time. And here also we provide an alternative source of EMF V is equal to Vm sin omega t in terms of sine function. So here we just represent the current generated in the capacitor in terms of sine function. So the current generated in a capacitor in terms of sine function, it becomes I is equal to Im sin 90 plus omega t. I is equal to Im sin 90 plus omega t. EMF is the same, V is equal to Vm sin omega t. And what do you think? Does the current and voltage are in the same phase?
No.
No. The value of the current and that of the voltage, they are not in the same phase. In the case of EMF, the phase angle is omega t. But in the case of current, the phase angle is 90 degree plus omega t. 90 degree plus omega t. So here also we can draw a conclusion. In the case of capacitor, current leads the EMF. Current leads the EMF by an angle of 90 degree. Just opposite to the case of inductor. In the case of inductor, current lags the EMF by an angle of 90 degree. But in the case of inductor, current leads the EMF by an angle of 90 degree. Here also I will give you a short method to study. Suppose I represents the value of current. I is represent current. Here I is leads. So we can write the current first. In the case of capacitor, so C is represents capacitor. And EMF is represented by the letter E. I's. So in the case of capacitor, current is first. Current leads the EMF. In the case of inductor, we have ELI. Here EMF leads the current by 90 degree. This is the EMF. Here we have the inductor. And this is current. In the case of inductor, EMF leads the current. In the case of capacitor, current leads EMF. Just a code to remember. So this is the one of the important conclusion that we are drawn in the case of AC voltage through a capacitor. If in the case of AC voltage through a capacitor, current leads the EMF by an angle of 90 degree. Okay, so that's all about the derivation of current in the case of AC voltage through capacitor. So the value of voltage is V is equal to Vm sin omega t, and the value of current is I is equal to Im sin omega t plus 90 or 90 plus omega t. Now what is our next step? The derivation of current is over. The next topic that comes under the AC voltage through capacitor.
Graphical representation.
Graphical representation. So write the next heading. Graphical representation of AC voltage through capacitor. Graphical representation of AC voltage through capacitor. So as we discussed earlier, here also we can construct a table for phase angle omega t for 0 degree, 90 degree, 180, 270 and 360. Voltage is the same. V is equal to Vm sin omega t. Then the value of current, I is equal to Im sin omega t plus 90. V is equal to Vm sin omega t. So the first phase angle is 0 degree. That is V is equal to Vm sin 0. What is sin 0? Sin 0 is 0. So we can write the alternate angles also will be equal to 0. Here it is 0. Here also it will become 0. So if we get the first angle, then we can easily write the another alternate angle. So here V is equal to Vm sin omega t, sin 0 equal to 0. So the alternate angles will be equal to 0. Now the next phase angle is 90 degree. Sin 90 is equal to 1. So V is equal to Vm into 1. That is Vm. So the alternate angle will be negative Vm, because sin 270, that is negative 1, Vm into negative 1, that is equal to minus Vm. Similarly, we can find out the value of current. The first phase angle is omega t is equal to 0 degree. So I is equal to Im sin omega t plus 90, where omega t is 0. So 0 plus 90, that is 90 degree, sin 90.
1.
1. So I is equal to Im into 1, that is plus Im. Then what about the alternate angles? If it is plus Im, the next one is the next alternate angle. Means 180 degree it becomes minus Im. Then for 360 it is again plus Im. What about the corresponding alternate angles? It becomes 0. So here we represent the phase angle in tabular form. Now we can easily draw the graph. So here we have x-axis. The phase angle omega t is represented along the x-axis. Current and EMF is taken along y-axis. Negative current and negative EMF is taken along negative y-axis. 0 degree, 90, 180, 270 and 360. First we can draw the graph corresponding to EMF. For 0 degree, the value of EMF is 0. For 90, it is plus Vm. 180 again 0. 270 it is negative Vm. And 360 it is 0. While joining all the points, we get a graph like this. The solid line represents EMF. Similarly, we can draw the graph corresponding to the value of current. In the case of current, it is starting from positive Im. For 0 degree, it is plus Im. 90, it is 0. Then again 180, negative Im. 270, it is 0. Then 360, it is positive Im. Dotted line represents the value of current. So this is the graphical representation for AC voltage through capacitor. From the graph itself, it is very clear that here the current leads the EMF. Current is starting from a positive Im value, but here the EMF is starting from 0. Is it over? graphical representation of AC voltage through capacitor. Then what about our next topic? Next subheading that comes under the AC voltage through capacitor. After the graphical representation, we have to discuss phasor diagram. So here we derive an expression for the current generated in a capacitor when an alternative source of EMF is connected to it. V is equal to Vm sin omega t. Then following that, we are draw the graphical representation. Then after this graphical representation, we are going to discuss the phasor diagram. Phasor diagram corresponding to AC voltage through capacitor. Phasor diagram for AC voltage through capacitor. Again, consider the same points here. We have 0 degree, 90 degree, 180, 270, and here 360. Phasor diagram is a diagram that is used to represent the phase angle with respect to origin. So here the alternative source of EMF will be the same, its phase angle omega t. V is equal to Vm sin omega t. That is, the EMF is deviated from the origin by an angle of omega t. So this represents V is equal to Vm sin omega t. The EMF is deviates by an angle of omega t with respect to the origin. Then what about the value of current?
On the second one.
Yes, current is leads the EMF by 90 degree. That is omega. I is equal to Im sin omega t plus 90 degree. It shifted omega t away from that of the 90 degree. Omega t plus 90 degree. It represents the phasor diagram for the current. I is equal to Im sin omega t plus 90. In the case of inductor, it is omega t minus 90. 90 degree that is subtracted from that of an angle of omega t. In the case of capacitor, it is omega t plus 90.
Ma'am,
Yes.
ma'am, that entire angle from 0 degree must be omega t plus 90, right?
Yeah. From this 0 degree to this, it is shifted from an origin at an angle of omega t.
No, ma'am, I.
Yes, from here. Yeah. Is it over?
Yes, ma'am.
Okay. So here we have one more graph. That's a special case for capacitor, as we told in the case of inductor. Here also we have a special case. Relation between capacitive reactance and frequency. Relation between capacitive reactance and frequency. What is capacitive reactance? Capacitive reactance is the resistance offered by the capacitor. It is represented by chi C. This is what is known as capacitive reactance. And what is the equation for calculating the capacitive reactance? Chi C is equal to capacitive reactance chi C is equal to,
C omega.
is it C omega?
1 by C omega.
1 by C omega. Chi C is equal to 1 by C omega. But we know that the value of omega. What is omega? Omega is equal to, as we told in the previous session, in the case of inductor, omega is equal to the relation between frequency and omega. Yes, omega is equal to 2 pi f. So chi C is equal to 1 by C omega, where omega is equal to 2 pi f. That is, the frequency is directly proportional to the omega. Then chi C becomes chi C. Chi C is equal to 1 by C 2 pi f. That is, the capacitive reactance is inversely proportional to frequency. Chi C is inversely proportional to f, whereby 1 by 2 pi C is a constant. So it becomes chi C is inversely proportional to 1 by f. Capacitive reactance inversely proportional to 1 by f. Then the graph will be, draw the frequency along the x-axis. Chi C is taken along the y-axis. Then the graph will be like this. Whenever the capacitive reactance increases, the value of frequency seems to be decreases. They are inversely proportional to each other. So in the case of capacitive reactance, it is inversely proportional to frequency. In the case of inductor, the inductive reactance is directly proportional to frequency. In that case, we get a straight line graph. Okay, is it over? Okay, that's all for today. Let me take your attendance.